Morning, everyone. We're a bit early. Any questions while we wait? Let's do it. Let's do it. First question to ask ourselves is, what is the limit of just secant x? Right? Because you know that the exponential function is continuous. So the limit of this is e to the limit of secant x, assuming this limit exists. Right? In other words, you can take the limit inside. This is by continuity of the function. So what is happening to secant x? Well, you know that secant x secant is just 1 over cosine. I think from the right, yes. We were missing something, limit from the right. Because that's very important here, because the limit itself did not exist, but the limit from the right does exist. So what is happening to the limit from the right? Well, you know that cosine of pi over 2 is 0. So this has the form 1 over 0. And in the context of limits, we understand this to be some sort of infinity. We only have to determine if it's positive infinity or negative infinity. But for numbers bigger than pi over 2, cosine is negative. The numerator is positive, cosine is negative, so the whole fraction is negative, negative infinity. So this is really e to the negative infinity. Negative exponent means 1 over. And here you're taking larger and larger powers of 2.71, which is going to be 1 over infinity, which is 0. Everybody with us here? Questions? Questions on something else? Allison's asking for allowed calculators on the quizzes and web work. Yes. Well, first of all, there are no quizzes, right? It's only going to be a midterm and a final. web work, it's fine. Although you should use web work as its own calculator, right? I mean, you never know how many decimal places web work requires. Go ahead and ask your web work problem. I mean, I don't want to answer it for you, but if you have, if there is an issue in understanding, we can address that. Is there new web work this week? Yes. How many questions on the midterm? I don't know. We're going to do it as a 3-hour midterm. So it really should take you less than 3 hours. But you will have the full 72 hours to do it. I want to say we already did that question in class. Square root of ln x over ln square root of x. What is your issue here? The midterm will not be timed. There are 2 solutions. Yes, that's fine. Maybe. I mean, it's not clear immediately that happens. Well, I mean, I don't know why there should be 1. Why should there only be 1? And here's what I'm going to suggest. In your work, when you did the work to find your 1 solution, if that's what happened, I'm going to suggest an assumption was made at some point. I'm going to assume an assumption was made at some point. And so go back and look at your steps carefully and ask yourself, was an assumption made in going from one step to the other? I'm quite certain that that's what happened. Olivia, you have 72 hours to open and to complete it. I mean, you can have the whole 72 hours, that's fine. All right, let's go back to what we were doing. Page wants us to prove there are roots. Well, you know how to do that, right? The intermediate value theorem is the key here. So we've done a few examples of those last time. Let me start you off, if I may. Bring everything to one side. No. Well, I mean, bring everything to one side by subtracting the x squared. Yeah, so bring the 0.01 x squared to the other side by subtracting. And then it's going to be the same thing as showing that expression on the left is equal to 0. And by the intermediate value theorem, all you have to do is, first of all, argue that your function is continuous, and then find values for which a function is positive and for which the function is negative. Since the 0 is between these 2 values, the function has to be 0 somewhere. So if that's what you meant by subbing in values, then exactly that. So we were looking at limits again last time, right? Limits at infinity. Let's do a few examples of things we saw. And you know what to do, right? I mean, if you blindly plug in infinity, we have an infinity over infinity here. And you know that to be an indeterminate value. So something's got to be done. What are you going to do? We're going to factor out x cubed from top and bottom. These cancel out nicely. As x goes to infinity, this goes to 0, this goes to 0, that goes to 0, and that goes to 0, leaving you with a limit of 1/2. Consider this. Again, as q goes to infinity, this has the form infinity over infinity. You know what to do. We're going to factor out something. There are different schools of thought here. Some people like to do one thing, others like to do the other. Whatever you want to do. What am I even talking about? I like to factor out the highest power in the numerator and the highest power in the denominator. Some people like to factor out the highest power combined. Other people like to factor out the smallest of the two. Whatever you want to do. It will all give us the same answer. But let me factor out the highest power in the numerator, which is q cubed, leaving us with that. And the highest power in the denominator, which is q squared, Sean is asking, how is this any different than using L'Hopital's rule? Well, you know L'Hopital's rule has to do with the derivative, and we haven't introduced the derivative yet. Well, I mean, still, I'm going to answer that. We haven't introduced the derivative yet, so we're far from understanding L'Hopital's rule. Moreover, as I suggested last time, L'Hopital's rule doesn't answer every single question. It's all good. L'Hopital's rule doesn't answer every single question. And the next question we're going to do, I'm going to invite you, Sean, to try it using L'Hopital's rule, and you can tell me what happens. This one, however, could have been answered using L'Hopital's rule. But first of all, let's cancel some stuff. The q cubed and the q squared cancel to leave you with just a q. As q goes to infinity, this goes to 0. This goes to 0, that goes to 0, that goes to 0. Denominator goes to 4, numerator, because of this q, goes to infinity. Infinity times 1. So numerator is infinity, denominator is 4, answer is infinity. That's it. Here's the question I was alluding to. Because, you know, I mean, it is an important question. People who have been introduced to L'Hopital's rule want to use that forever and always. But the truth of the matter is, while it's a very powerful tool, it doesn't answer every single question. And here we're looking at different techniques which are very important in themselves. Consider this. So Sean, I'm going to invite you to apply L'Hopital's rule. See what happens. Right? As x goes to negative infinity, first of all, when you just blindly plug that in, this is infinity. Square root of infinity is infinity. And here negative infinity cubed is negative infinity. With this negative makes everything positive, but it doesn't matter. It's still an infinity over infinity. Oh, I mean, no, nobody's getting called out. It's all good. I mean, it's part of the learning process. And again, for, you know, I say Sean because he's the one who asked the question, but anybody who's tempted to use L'Hopital's rule is invited to try this question using L'Hopital's rule. If you don't know what L'Hopital's rule is because you've never seen it, and that's completely fine, and forget this discussion. Do it the usual way. But again, those who've seen L'Hopital's rule want to use it always, but it doesn't work here. Right? This has the form infinity over infinity. So you know this to be an indeterminate form. What are we going to do? Well, you know what to do. We're going to factor out the highest power in both the numerator and the denominator. So we'll factor out an x to the 6 here. This is 1 over x to the 6 plus 4. And we'll factor out an x cubed in the bottom. There we go. Well, we already have two answers. Unfortunately, they're not equal. So which one is it? And is the answer to the last question equal to 4? No, the answer is infinity. We had a q cubed in the numerator and q squared in the denominator. So after cancellation, there was a q left in the numerator, and as q goes to infinity, numerator went to infinity. So Rachel is actually asking, is the answer q over 4? You shouldn't write that, because where do you get q over 4 from? You get it after having taken the limits of these things. Now, you're taking a limit of the whole thing. You don't want to take just limit of part of it and not the whole thing. So this q over 4, you should never actually write down. Let's finish that up. You know what to do. Limit as x goes to negative infinity. The square root of a product is the product of the square roots. And you know the square root of x to the 6 is absolute value of x cubed. Right, we discussed that last time. And absolute value of x cubed, since x is negative here, you know what's going on. This is actually negative x cubed. Now you can cancel these. As x goes to infinity, this goes to 0. That goes to 0. So you're left with square root of 4 is 2. So negative 2 over negative 1, which is 2 as suggested by Shamir. How are we doing? We do the absolute value because here there's nothing mentioned in front of the square root. So it's understood to be the positive square root only, right? There's no plus or minus here, or more importantly, there's no minus. So it's understood to be the plus. So here, whatever answer you plug in for x, you're going to get a positive number. So it has to travel forward, right? It could not be negative 2 because the plus or minus is not a function. And we're only dealing with functions. So, yeah, right? The square root of x squared is absolute value of x. That's what I'm using here because the left-hand side is always positive. So the right-hand side has to be positive as well. Everything is fine if x is positive and you just say square root of x squared is x, but you run into problems if you're taking negative values of x. And I was asking why we change it to negative. Well, we saw that the absolute value of x had this nice piecewise defined function, right? If x is positive, this was just x. But if x is negative, this is negative x. So we can get rid of the absolute value using this piecewise defined function. And absolute value of x cubed is either going to be x cubed if x is positive, or negative x cubed if x is negative, and there it is, because we are dealing with negative values. Why does the 4 square root become negative? Well, because of this negative right here. If it wasn't x to the 6, but x to the 5, then we wouldn't, and you can't take the absolute value. Well, I mean, first of all, you can always take the absolute value. But in that case, if it was a 5, then this would become 5 over 2. And this would only have been defined for positive values anyways. So the absolute value would not have been necessary here because the understanding would have been that we would have been dealing with positive values nonetheless, and this question would not have made any sense. Let's move on. By going back to a few indeterminate forms we saw. What did we see as far as indeterminate forms? And first of all, what does an indeterminate form actually mean? It means that we cannot determine the value of the limit just by knowing it has this form. 0 over 0, we saw that that was an issue. Infinity over infinity, we saw that that was an issue, right? I mean, you should have examples immediately in your head that pop up to convince yourself that 0 over 0 and infinity over infinity are indeterminate forms. Also, we saw infinity times 0, right? Because you can break that up into infinity times 1 over infinity. And those same examples immediately work. So we saw these 3 indeterminate forms. Whether or not it's positive or negative makes no difference here, because you know you can always factor out constants from a limit. So you could factor out a negative from there, and we're good to go. So we have discussed these 3 indeterminate forms, and again, I cannot help but stress the fact that you should have, as I'm speaking now, examples popping up in your head of limits 0 over 0, which can give you anything you want. Infinity over infinity, which can give you anything you want. Infinity times 0, which gives you anything you want. Let's consider another one. Infinity minus infinity. Let me convince you that infinity minus infinity is yet another indeterminate form. With this simple example. As x goes to infinity, this goes to infinity, that goes to infinity, so you have the form infinity minus infinity. What is the limit here? If you open up the brackets, the x cancel and you're left with just 1. Sean is asking for an infinity times 0 example. We'll do one. But you see where I'm going with this? Right? This limit is 1, and then change that 1 to a 4. It's still infinity minus infinity. Change that 4 to a 42. It's still infinity minus infinity, and so on and so on. Is minus infinity over infinity indeterminate? The answer is yes. Doesn't matter the sign here. Still indeterminate. So is everybody comfortable with the fact that infinity minus infinity is yet another indeterminate form? Let's do an example of infinity times 0. And before we do an example of infinity times 0, let's go back to infinity over infinity, because the same example works. Right? This limit is 1. But then if you change that to a 4, it's still infinity over infinity, and that is 4, and so on and so on. So you see why it's indeterminate. Rearrange this. X times 1 over x. Then as x goes to infinity, this goes to 0. So this has the form infinity times 0. But of course, this limit is the same as the original we had. This is 1. And if you change that to a 4, it's still infinity times 0. But now the limit is 4, and so on and so on. Convinced? So what? So what is a good question. 0 to the 0 is also an indeterminate form, absolutely. Let's not discuss that yet, though, because we're ill-equipped to treat that. Sean is asking, why is 1 over infinity 0? Well, you tell me. We've been using that over and over again, right? 1 over infinity, think of infinity as a large number that gets larger and larger and larger. These fractions are getting smaller and smaller, closer and closer to 0. Indeterminate, Mara, only refers to the form. Just by knowing the limit has the form 0 over 0, you cannot determine what the answer is. Just by knowing the limit has the form infinity over infinity, you cannot determine what the answer is. Anything can happen. But now, faced with a problem that has this form, you have to do some work. Consider this. And Jordan's asking, would 1 over 0 in comparison be infinity? Well, in the context of limits, exactly that. 1 over 0 is some sort of infinity. It could be positive or it could be negative. We have to figure that out. Consider this. The first question, so, you're taking a limit. It's actually not 30. I rearranged it a bit. You're taking a limit as x goes to infinity. So, what we like to do is plug in, see what happens. And if you plug that into here, you get infinity minus infinity, which you know to be an indeterminate form. So first, let's talk about the stuff in the square root. What is happening to that? This has the form infinity minus infinity. It's indeterminate. Something's got to be done. What are we going to do? What are we going to do to decide what limit that is? Let's factor out. Let's factor out an x squared. The usual, right? Even though it's not in a fraction, it can still factor out. And now you see what happens. As x goes to infinity, this goes to 0. So the stuff in the brackets goes to 4. This goes to infinity. So the answer is infinity. The square root is still there. I'm just having a look at the inside because it had the form infinity minus infinity. So the stuff inside goes to infinity. It's just an aside, Guillaume. We're just having a look at the inside of the square root. I did not put these as being equal. We're just having a look at part of the problem. But now we have concluded we are not ignoring anything. We are just looking at this. Only to understand that this goes to infinity. Square root of infinity is infinity. So now we understand that this limit has the form infinity minus infinity. Is everybody comfortable with that? And Darren is asking, what if it was negative infinity? Well, I'm going to let you work that out. All right. Now that we have convinced ourselves that we have infinity minus infinity, this is an indeterminate form. Something needs to be done. We cannot determine what the answer is just by knowing that it has this form. We need to do something. What are we going to do? We've seen this trick before. We're going to multiply by 1. If you multiply by 1, you don't change anything. So multiplying by 1 doesn't have an effect on the answer. What 1 am I talking about? I'm talking about the conjugate. Did we see that that happened before? I forget now, because I am teaching another course in which we do limits. It might have been the other course. Regardless, we did see it. Thank you. Very well. So multiplication by 1. You're multiplying by 1, right? You're multiplying by an expression over itself. So this is just 1. When you multiply by 1, you don't change anything. What does that do in our case? Well, the square root times the square root. Square root disappears. Square root times positive 2x. And then you have the square root times negative 2x. So those disappear as well. Right? You have 2x times the square root minus 2x times the square root. So that's gone. And finally, minus 4x squared. Multiplied by the conjugate has the effect, buffer already, has the effect that you get rid of the square root. Denominator is this. And there it is. Very good. The 4x squares cancel out nicely. So now we have a 3x over this. Let's see what happens when x goes to infinity. Clearly, numerator goes to infinity. It's actually negative infinity, but it doesn't matter. Well, it's unfortunate if it's laggy. But, you know, I mean, I've been posting the downloaded lectures, so you can always refer to those. And what happens as x goes to positive infinity? Well, we just saw that this part goes to infinity, square root of which is infinity, plus 2 times infinity, which is infinity. So infinity plus infinity is infinity again. So we had an infinity minus infinity. We multiplied by the conjugate. And now we have infinity over infinity. Still indeterminate. We still have to do some work. But now it's a bit easier. I think it's clear what the work is. Numerator is negative 3x. We're going to factor out an x squared. from the square root. And once again, if you were tempted to use L'Hopital's rule here, even though I don't want you to do that, but it's always tempting, L'Hopital's rule will not help you here. So it's important that you are familiar with these other techniques. Well, I mean, as Kelly points out, it's actually negative infinity over infinity here, but it doesn't matter, right? It's still an indeterminate form. The sign of the infinity does not matter. The minus 3x doesn't become positive infinity because it's minus 3 times infinity. Let's finish that up. Square root of a product is the product of the square roots. And square root of x squared is the absolute value of x. Right? It's the absolute value of x. And in this case, x goes to infinity. So x is positive, and absolute value of x is just going to be x in this case. Having done that now, we can factor out an x from the denominator. The x's cancel. As x goes to infinity, 3 over x goes to 0, leaving us with minus 3 over 4. How are we doing? Why don't we consider the following example? It is asking us to find vertical and horizontal asymptotes. If any, where the function is this. How did we factor out an x from the 2x? Well, you have an x both in here. Right, I mean, this is really x times something plus 2x times something, so why don't we call it ax plus 2x, right, where this is a. Now you've got an x there, so factor out an x. A plus 2, a plus 2. Find vertical and horizontal asymptotes. Isn't the x from the root of x squared? Absolutely, right? Square root of x squared is x in this case. It's really absolute value of x, but yeah. Would you also have to factor it out? Wow. Somebody want to address that? From the 3 over x though? Right, I mean, here's the answer to that. Find vertical and horizontal asymptotes, if any. You know what these things mean, right? What are horizontal? Well, let's start with the vertical, since that's what came first. What are vertical asymptotes? What is the definition of a vertical asymptote? X equals A is a vertical asymptote if what? If the limit as x goes to A from the left or from the right of some function is equal to some sort of infinity. Are you saying this x should be x squared? But it's square root, right? So x equals A is a vertical asymptote if the limit is some sort of infinity. Here we're looking at this function. This is your function f. And the question is, when is this infinity? Negative or positive? When does this blow up? And in the context of limits, you know a limit is infinity if you have a limit that has the form of a non-zero number divided by 0. Okay, we need to go back to what's happening here. Why is there confusion? Why is there confusion about the previous question? Where did I lose you? Anybody? Stop me now. Right? The justification is right here. This is x times a plus 2x. If I factor out an x, what happened to the 2? The 2 is still there. And as x goes to infinity, this goes to 0, so you have square root of 4, which is 2. 2 plus 2, which is 4. Last 3 steps. So what did we have before? We had limit as x goes to infinity of minus 3x over the square root of 4x squared minus 3x plus 2x. This is what we had after multiplication by the conjugate. Is everybody comfortable with that? And this still has the form, well, not still, but this has the form infinity over infinity, which you know to be an indeterminate form. So something's got to be done. What are we going to do? We're going to factor out an x squared from here. And now you're going to take that out of the square root. Square root of x squared is absolute value of x in general. But here, since you're dealing with positive values, it's just x. The confusion is why 2x becomes 2. Well, just multiply the x back. It's x times this plus x times that. Exactly that. Exactly as Benjamin suggests, x square root plus 2x is x times the square root plus 2. Exactly what I stated here. Right? Now you've got an x in here and an x in there. I'm going to factor out x from the whole thing. So it's x times the square root, as Benjamin suggests, plus 2. And then you can cancel the x's. How are we doing here? Questions? And then once the x's are canceled, well, the limit itself is trivial. Let's look at the vertical and horizontal asymptotes, right? We're looking for vertical first, so we need where the denominator is 0. Does this factor? Does this factor as 3x and x? Maybe it does, maybe it doesn't. 3x plus 1 minus 1. 3x squared plus 3x minus x is a plus 2x and minus 1, very nice. And so now what? We have to search for vertical asymptotes when the denominator is 0, so at minus 1 and at 1/3. Are possible vertical asymptotes. They're not immediate, right? We have to check that we have this, right? Just because the denominator is 0 there doesn't immediately imply that we have vertical asymptotes. Let's verify. Limit as x goes to minus 1 from the left. Numerator is going to be close to 3. This is going to be close to minus 4. And a number less than 1, less than negative 1, plus 1 is negative, but it's going to be 0, right? So we have a 3 over 0, so we know it's going to be some sort of infinity. Numerator is positive, this is negative, and this is negative. So the whole thing is positive, positive infinity, and we're done. Negative 1 is a vertical asymptote. What about right? I mean, you don't even need to check the other side. One side is sufficient. As soon as one side blows up, that's enough. You could check from the left, you don't need to. As soon as one side, well, actually the left is what we did. You could check from the right, and whatever you get, whatever answer you get, it's immaterial because you already have infinity there. And now if x is 1/3, let's see what happens there. Let's do it from the right this time, no reason. Only to illustrate the fact that as long as one side blows up, that's enough. As Michael has suggested, the other side gives you negative infinity. That's because he worked it out. He did not assume that the limits change sides, that the limits rather change signs. He did not make that assumption. Instead, he worked it out and told us that it will give us negative infinity, and that is correct. And here, when you plug in 1/3, this is 1 plus 2/9. This is 0, and this is 4/3. So this has the form 1 plus 4/9/0. In other words, some sort of infinity. We need to determine if it's positive or negative. Numerator is positive. This is going to be close to 4/3. And a number bigger than 1/3 times 3 is going to be bigger than 1. Minus 1 is going to be positive again. So everything is positive here. Positive, positive, positive. We have an answer of positive infinity. So x equals 1/3 is a vertical asymptote. What about horizontal asymptotes? For a horizontal asymptote, Matthew's asking if it even matters to figure out if it's positive or negative. You're correct, it really doesn't matter. But we should. We should to make it complete. Yeah. Because what if the limit actually doesn't exist? And I mean, it's questionable what is actually happening there. X plus 1 is not negative here, it's positive. This is positive, this is positive, this is positive, everything's positive. For horizontal asymptotes, what are we looking at? We look at the behavior of the function as x goes to infinity. So what was our function? This is our function. Why not check 1/3 from the left? You can check it. You can check it. But as soon as we have one infinity, whether it's positive or negative, that is it for vertical asymptotes. So whatever happens on the left is immaterial. We already know that it's a vertical asymptote. For horizontal asymptotes, limit as x goes to infinity and negative infinity, right? As x goes to infinity, this has the form infinity over infinity. You know what to do. I'm going to factor out The x squares cancel out nicely. As x goes to infinity, this goes to 0. This goes to 0. This goes to 0, leaving us with a limit of 2/3. i.e. y equals 2/3 is a horizontal asymptote. We also need to check the other one. Absolutely. We need to check negative infinity as well, because it could actually yield a different answer. Right? This is the behavior for large positive values. There's no telling what happens for large negative values. The behavior of the function for large positive values does in no way affect the behavior for large negatives. Anything can happen there. In particular, we may have the same horizontal asymptote. We could have a different horizontal asymptote. We might not have any horizontal asymptote. Who knows? But here, you still have the form infinity over infinity, and doing exactly the same thing works. The x squares cancel. This goes to 0, that goes to 0, that goes to 0, leaving you with 2/3 again. Benjamin is asking, isn't it enough that the denominator is 0? Can we not conclude that you have vertical asymptotes there? The answer is no. No. No, because what if you had, here's an example. X squared minus 1 over 3x squared plus 2x minus 1. If you have this example, if you had this example, so Benjamin, I'll invite you to try this example. You might be tempted to believe that, right, since the denominator is exactly the same, x equals 1/3 and x equals -1 are vertical asymptotes, but they are not. They are not. 1/3 is a vertical asymptote, but -1 is not. Try it, see what happens. And Jude is asking, will it always hold that if the degree of the numerator and denominator are the same? All right, we're back. Excellent. Let's wait maybe a few seconds until everybody is back. So now that we have mastered, well, Jordan is asking exactly the same question as somebody was asking before, the buffer. You're right that this can be done. Let us not use that as a rule, though. On an exam, I want to see all the work as we did. So we never made use of that property, and you shouldn't either. I mean, you can keep it in the back of your head to to make sure that you end up with the right answer, but let's not use it. So now that we have mastered limits, let us go back to what led us to the study of limits. And the idea was that we wanted to import the idea of a tangent line. We wanted to import the idea of a tangent line to functions, right? Locally, you can think of this as being part of a circle, if you will. And the tangent line is a point that intersects a circle just at one point. So we're generalizing this idea to functions. We're looking for a point, for a line at the point x, so at the point xf of x, which just touches the curve at one point. What led us to the study of limits was our realization that if you consider another point, maybe x plus h, and look at the line joining those 2 points, this could be viewed as an approximation to our tangent line, albeit a terrible, terrible approximation. Right? This is the point x plus h, f of x plus h. And if we look at the slope of the line joining these 2 points, the slope of the line, change in y divided by the change in x, f of x plus h minus f of x over x plus h minus x, or if you prefer, f of x plus h minus f of x over h. This is a terrible approximation, but if you take h smaller and smaller, you get a better and better approximation. So our goal was to ask the question, what is happening to this expression as h gets smaller and smaller, closer and closer to 0. That brought us to the study of limits before we move on to the study of this expression. But now that we have understood limits, we're ready to study this. So let me introduce a definition. Given a function, f of x, we define the derivative denoted f prime of x to be the limit as h goes to 0 of f of x plus h minus f of x over h. Jennifer is asking if you'll be submitting pictures of our answers on an exam. The answer is yes. Exactly that. right? So we're defining now the derivative of a function. We're defining the derivative of the function as this limit. And you've understood where this comes from, right? The derivative gives us a rule for the slope of the tangent line. Right? That's what the derivative is. It's a rule for the slope of the tangent line. Also, right, it was delta y over delta x, so the change in y, right, this is the change in y divided by the change in x. So the derivative is sometimes referred to as the instantaneous rate of change. It's the rate of change of the function precisely at the point x. Let's take a few examples. If the function is 3x plus 7, let us find the derivative. By definition, the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. So everywhere you see, Sheridan is asking, what does h represent? From the graph here, right, this is x plus h. H is just a quantity. Just a quantity. It's just a quantity that makes x plus h differ from x. What we're looking for is the behavior as h gets smaller and smaller. As h gets smaller and smaller, you get a better and better approximation to the slope of the tangent line. So we're asking the question, what is the behavior as h goes to 0? What is the limit as h goes to 0? F of x plus h, everywhere you see an x in your function, replaced by x plus h. This is 3 times x plus h plus 7 minus the function 3x plus 7 over h. Expand everything, simplify. This is 3x plus 3h plus 7. Distribute the negative, minus 3x minus 7 over h. The 7's cancel out. The 3x's cancel out, leaving you with 3h over h. The h's cancel out, leaving you with a limit of 3. As Benjamin suggested, the derivative of 3x plus 7 is 3. How are we doing? Let's try another one. square root of x. Same question, find the derivative. So again, the derivative is just the limit as h goes to 0 of this. Well, we have two different answers there. We'll see what happens. Let's do it together. F of x plus h, everywhere you see an x in your function, replace by x plus h. What do we get? Square root of x plus h minus square root of x all over h. Now what? Now what do we do? How do we evaluate this limit? Because you know what to do, right? I mean, we've seen limits before. When dealing with a limit, first thing to do is plug in. And if you plug in, what are we looking at? If you plug in h equal to 0, what does this limit look like? If you plug in h equal to 0, the numerator is 0, the denominator is 0. This has a form 0 over 0, which is an indeterminate form, right? And I mean, just look back to this. If h is 0, you get f of x minus f of x, which is 0 over 0. It's always a 0 over 0 form. This is why we were studying limits to begin with, right? To figure out what to do in these cases. And as few people have suggested, we'll multiply by the conjugate. Multiply by 1. When you multiply by 1, you don't change anything. So multiply by 1. And what does that do? You've seen what that does, right? That gets rid of the square root in the numerator. This is x plus h minus x. Right? I mean, just expand this times this, and then plus the 2 square roots, and then you get minus the 2 square roots, so those cancel out. And then root x times root x, which is just x. And now the x's cancel, leaving you with what? Leaving you with h over h square root of x plus h plus square root of x. Now the h's cancel, And as h goes to 0, this goes to 0. So you get a 1 over 2 root x. Right? You get a root x plus root x, 2 root x, 1 over 2 root x. How we doing? Shall we try one from the book? Can we explain the last step, the plugging in of the h? I mean, you know limits, right? The first thing you want to do is plug in. Plug in and see what happens. If you don't have an indeterminate form, you're done. After canceling the h's, right? Because that was what was giving you a 0 over 0. These cancel out. Numerator is 1. When h is 0, that goes to 0. So you get a root x plus root x, 2 root x. Let's repeat with this. Same question. We're looking for the derivative. What is the derivative? So the derivative, by definition, limit as h goes to 0 of f of x plus h minus f of x over h. What is that? In this case, f of x plus h, everywhere you see an x in your function, replace with x plus h. What do we have? X plus h over x plus h plus 2 minus f of x all over h. What are you going to do? What are we going to do? We're subtracting two fractions here. Probably makes a lot of sense to put everything over a common denominator. Let's do it. What is a common denominator? Common denominator is going to be the product. Right? Some of you may be tempted to try and squeeze in an h, because that's all you're missing here, but it's impossible to bring a plus h into this denominator. The common denominator is the product of the two. So here we're missing an x plus 2. And over there we're missing an x plus h plus 2. I'm dividing by h here. Where does the h go? On top or on the bottom? Top or bottom? Where does it go? You tell me. Let me expand this. X squared plus 2x plus hx plus 2h minus x squared minus xh minus 2x over and where did we say the h goes? I'm seeing bottom denominator. Exactly that. The x squares cancel out. The xh and xh and hx cancel out. The two x's cancel out, leaving you with an 2h in the numerator. And this business in the denominator. Now you can cancel the h's. And as h goes to 0, that goes to 0, that goes to 0, leaving you with a limit of 2 over x times x plus 2. Very nice. Is that right? What was the original function? We had x over x plus 2. Yeah, that's not right at all. What happened? What happened? Where's the mistake? The x plus 2 in the bottom turned into x plus h. There we go. X plus 2. Thank you. This is x plus 2. So this is not correct. What is that? This goes to 0, so we get a 2 over x plus 2 all squared. There we go. That's right. Thank you. There it is. So look, here's the thing. I know some of you have some experience with the derivative, and you may be able to find the derivative using other techniques. It's very important that you be able to find the derivative using the definition. This is of crucial importance. This is what gave rise to the whole study of the derivative. So practice this today, tonight, tomorrow. We'll pick this up again on Friday. Thank you all for coming. I'll see you guys then. I've posted office hours if you need to see me, Monday or Wednesday. Monday, Wednesday after class. I'll open up. I think we're ready for the next web work. I'll open it up today. Very good. I'll see you guys on Friday.